Hello, everyone. Thanks for joining. My name is Animesh Singh, and here is my co-speaker, Svetlana Levitan. We are part of a group in IBM called CODE, Center for Open Source Data and AI Technologies. Our mission is to work on open source technologies throughout the AI lifecycle. That means, through the data phase, which is, the data preparation, model training, model serving, model management. And there are various open source projects which we have launched, plus there are various open source projects which we work and contribute to in the community, including Spark. IBM was one of the top 5 contributors in Spark last year. We contribute to TensorFlow, PyTorch, Onyx, a lot of projects in this ecosystem. And the main mission of our group is essentially work around the 3 pillars of code, content, and community. Contribute code to the open source, create relevant content for consumption of that, and then definitely make sure we are working in the community with the community members. So before going into the details of the particular topic where we are going to talk about how to defend your deep learning models from adversarial attacks, I just want to give a brief history. For me, it was in 1997 when I actually became aware of the term artificial intelligence in general, where IBM's Deep Blue beat Garry Kasparov in chess. That was back in India. And when I was here, the next seminal moment was 2011 when Watson actually beat the Jeopardy champions. Something very recently, which we probably all have seen, is DeepMind's AlphaGo beating Lee Sedol in game of Go. And just last year, IBM launched Debater, right, which actually goes into the realms of common sense reasoning, and it actually held very convincing arguments with a lot of rational thoughts, against professional debaters, right? So this is now AI going into common sense reasoning. So if you look at the progress of deep learning, it was not until 2012, when AlexNet introduced deep learning with GPUs, when this started taking off. And I would say, 2015, when Facebook widely adopted it for its image recognition technology, that was the seminal moment when it actually, became very widespread. What is deep learning? Essentially, in very simplistic terms, we are training artificial neural networks. If you think of neural networks or what is a neuron, it's essentially think of it as a calculator. You give it as an input, it has certain functions and provides you an output. Now, if you look at the capacity, which deep learning has achieved, around 25 million neurons, 100 million connections. Now, when we compare it with a human brain, which has around 200 billion neurons and 32 trillion connections, we probably have achieved around 0.003% of what a human brain can do. But in spite of being able to do so less than what a human brain is capable of, the advancements and the capabilities which deep learning has provided have been humongous. Now let's talk a bit about the machine learning workflow in general and where does model validation and model security fits in. Now the general perception is that you have data, you apply machine learning, and you get dollars, right? I mean that's essentially how a lot of the folks start approaching it, more so from the top-down level. But when you actually, look under the hoods, you see, there is a lot of work involved in terms of, preparing the data visualization, feature transformation, engineering, selecting the model, the right hyperparameters, then, being able to train those models, deploy it, and once you have deployed it, being able to monitor the predictions are correct, it's working, against the real-world data in a manner which is fair. So if you look at the neural network design workflow, essentially, you design your initial neural network, you assign hyperparameters, you point to domain data, and you train, right? If your performance meets the need, you are good. If not, then you assign additional hyperparameters and start another experiment, right? And if it does meet the need, you deploy, but your job doesn't end there, right? You are actually continuously monitoring the model's predictions in real world to see, if it is giving the right predictions, is it vulnerable to adversarial attacks, etc. So, I mean, this is, high-level view of the AI workflow in general. If you look at, at the very beginning, in terms of beyond the data phase, right, where Spark plays an important role, But in just, where do you create initial models, a lot of tools have come in. To assign your hyperparameters and train, there are various libraries which have been popular in the machine learning world, like, TensorFlow, scikit-learn, XGBoost. But what has also happened is, because of the proliferation of these libraries, how do you actually approach them in a consistent way and standardized manner? That has become a problem because normally, within big enterprises, you have teams, who are using different libraries for different models which they are preparing. Right, so for that, last year, we launched FfDL, Fabric for Deep Learning, and it actually, essentially provides a consistent interface on top of multiple frameworks, TensorFlow, PyTorch, Caffe, etc. And then we also integrated, a lot of the machine learning capabilities. We worked with S2.ai to get their machine learning algorithms integrated in it. We worked with Uber to get their distributed training mechanism, right, which optimizes GPU to GPU communication across multiple machines integrated as part of it. We actually worked with Facebook and launched PyTorch 1.0 support on the same day, when PyTorch 1.0 was announced, right? So the idea for Fabric for Deep Learning is, consistent distributed deep learning training on top of Kubernetes. So now when we look at this next phase of the life cycle, right, where do you deploy your models? There are there are various options which are emerging in open source. Selden is a platform where you can actually deploy a lot of the machine learning as well as deep learning models, right? So if we go now next, are these, phases in these life cycle, right, which is beyond, creating your model, deploying your model, is essentially, how is the quality of your model, right? So essentially, when we look at it, right, there are three things, right? So one is, from a trusted AI perspective, can your data set be trusted? Is the model vulnerable to adversarial attacks? Can the trained model be trusted? If your model is giving predictions, right, can it explain what it is doing? There are a lot of these factors which actually, open up the black box of AI. So for us, what does it take to trust a decision made by a machine? Is it fair? Easy to understand? Can anybody tamper with it very easily? Is it accountable? So those form the tenets of our trusted AI, what we call, fairness, explainability, robustness, assurance. Now, today's topic, the place where we are going to go deep is around robustness, but, there are various tools, and I will touch on them a bit around, different things. So, for example, bias, right? This is a topic which is, very relevant. There is a lot of discussion around, how do you make sure, your data set is not biased, the model classifiers and the weights, which are coming from human perception, right? They are not biased, or even once your model is trained and deployed, the predictions it is giving, they are not biased. Right, so for that, we actually launched a tool in open source called AI Fairness 360, in short, AIF 360. And the goal there is that, it's an open source library to actually, be able to detect bias in your data sets, in your model weights and the classifiers, and also, once your models are deployed, monitor the predictions, right? It has around 70 plus fairness metrics against which it detects whether there is, the model is fair. And then if my models or, the data sets are found to be biased, there are around, 10 mitigation algorithms. So it not only detects, right, it provides mitigation algorithms which you can use. It's available on GitHub at github.com/IBM/AF360. And as I mentioned, right, there are 70 plus metrics against which it detects bias, right? So it could be, is it fair for an individual? Is it fair for a group? Right, within those criteria, right, all these different metrics work. If you want more details, right, if you go to the GitHub, there is a site to, there is a link to our main, web demo where you can actually see that. And then once it finds bias, right, it has around 10 bias mitigation algorithms, which you can actually use to apply against, your data set or your model weights and classifiers, and then, be able to mitigate bias in those. This is the link to actually go if you are interested in this topic. This is public URL, AIF360.mybluemix.net. It has all the different metrics listed, the algorithms listed, explanations for them, and actually walks you through the demonstration, what, if you can point to a particular data set, detect bias. If you detect bias, how do you actually remediate it? So we talked about, the bias part. Now let's talk about robustness, right? So there are various things, right, which can happen, right? Is the data set which you are using for your model training, is it poisoned? Is the model which you have produced, right, is it vulnerable to adversarial attacks? So can an adversary come and, create, adversarial samples and point to your model, and it starts giving, predictions which are not accurate? So essentially, the field has been very active, right? I mean, adversarial noise and being able to generate adversarial samples which can fool a model. Now it's, it's a very wide attack spectrum which is being used, more so with institutions, where the rewards can be big, if you use adversarial attack on those, right? So I'll go into some of those. But if you look at something like scarier example, right, which is, let's talk about self-driving cars, right? So the way they are trained, to recognize stop sign is, they're given stop signs images, right? And they're being trained to actually recognize it and be able to stop when you see one, right? Now, if you just, perturb these images or generate adversarial samples, with even little noise, which can be at times, undetectable to human eye. In most of the cases, those are undetectable. The prediction of the model can be totally awry, right? In this case, as you can see, the self-driving car will not stop at a stop sign because it recognizes, it's setting it a speed limit. There is another, research paper which essentially, if, for example, there is a pedestrian crossing, right, and you're trying to cross, the self-driving car is going through that, right, and if you generate adversarial noise, right, and create an image sample, right, which actually hides, or, the model actually tends to think there are no pedestrians. Again, the results can be disastrous in this case. So when we look at adversarial threats to AI, right, I mean, definitely, the first place to start would be something like poisoning attack, where you essentially, insert poison samples in training data, right? The goal there would be, as long as, you are able to poison the training data, then you can actually use that backdoor later to exploit that vulnerability. The second would be, evasion attacks, which is essentially performed either at test time or, once your models are deployed, which is essentially, doing attacks to see that, if we generate adversarial samples and point to your models, are they able to, give accurate predictions? If they are not, that can be exploited, for various things. So there are various threat models, which are emerging in the industry, right? Definitely for attackers, the goal is to figure out, where they can attack. Is the AI system or, the deployed model, is it a black box where the only place they can start attacking is, from a deployed model perspective, or, they have backdoors, where they can actually, where they actually have access to, some of the training data, or, so they can introduce attacks much earlier in the AI lifecycle, right? The other thing is, type 1 versus type 2 errors, right? I mean, a lot of the times, the attackers can actually just be trying to cause, false alarms, right? So in those cases, what is the cost for the particular entity which is hosting those models, right, with those false alarms, right? Because their goal is to actually, put you in panic mode, right, while they actually are trying to do something else, right? And then definitely, the poisoning part, right, which is essentially if they have access to the data on which you are training, right? I mean, that's essentially, being able to poison the model, or the model which is being created, is vulnerable right from the offset. If you look at evasion attacks, generally, why do they exist, right? Typically, unless your test error is 0%, there is always a possibility, right? The attackers are actually, pushing you across a decision boundary. So, in a case of a simple model, right, if it is a classifier which is, classifying an object either into one group versus another, right, there is a boundary through that linear extrapolation, right, where actually they can cause confusion, right? So that's an area which they exploit. The other thing which they actually exploit is essentially, linearity hypothesis. So that means, I mean, if you see neural networks, they extrapolate linearly as a function of their inputs, right? So the goal of the adversarial examples is to push these deep neural networks, outside their designated operating range, right? And they form a subspace in that context, right? So it's not exactly a linear extrapolation in that particular case. The other thing is, typically deep neural networks, the general perception is, they are being trained to recognize something. But the idea is, we are training them to not, we are training them to actually discriminate, from a set of things, right? So if you're giving 5 objects, right, what they are saying is, which of the 5 objects don't fit within that model, right? They are not actually, trained to recognize. They are trained to discriminate. So for example, in this case, if they are trained to recognize or discriminate against anything which doesn't look like a school bus, as long as you can produce an adversarial sample which is very similar to a school bus, the chances of you being able to fool that model go very high. So now that we see, there are various attack methodologies, right? How do we actually defend, right? So there are various techniques in research papers, right, which are available, and various research papers have been written. It's a very active, field. But, the model hardening part, right, which is essentially, fixing the data at the pre-processing part, doing adversarial training, assigning robustness metrics, and then, having detector networks, right? So I'm going to go into some of these very quickly. So adversarial training, right? The idea is that we train our deep neural networks solely on adversarial samples, right? So that actually, in turn, increases your neural network's capability to actually maintain accuracy on a clean data, right? So that's a technique which a lot of people actually use. They explicitly and knowingly introduce, poison data and then train on that so as to make sure that, all the vulnerabilities are being found as the model is being created. Pre-processing data, right? The other thing is, if you're taking some standard data set, right, a lot of the techniques around, pre-processing data where you're actually processing samples in order to remove the adversarial noise, right? And then you are making sure, what you are, giving to your model to train on are actually clean data, right? So essentially, if the data set is coming from some public perspective, you are making sure that, you're removing all the poison part from there. The other aspect which I talked about was, the robustness metrics. So for example, this is an algorithm which was contributed by IBM research, and it's being used in some of our products as well. And the idea there is essentially that, you give some robustness metrics of around, different inputs and say, which one is, and you give them scores, and based on, the one which has the lowest score is the most likely to be able to fool a model, right? So in this case, if you see, and this is a scenario, right, for example, when you are giving your check images through your phones to banks, right? So if you see, in this case, the 4 in the middle has a score of 1.0457, which is the least. So that means, if I can change that slightly, that number, I should be able to, fool the banking system, right? And that might work, right? So in this case, right, if, for example, we perturb a little bit and then try to submit that check, the bank, instead of, thinking it's $461, you get credited for $961, right? So now you can see, even in real world, beyond, the self-driving cars, the financial institutions, et cetera, they can have, they can be severely impacted because of these things, if an attacker is clever enough to figure out, where the surface area is most vulnerable. Definitely, there are actually methods to defend against poisoning detection. So you actually look at, the clustering of the training data. And as you actually have those graphs pointed, you will particularly see a pattern, right, that the poison data actually, appears outside the normal clustering range within that data. And that's one clear indicator that, the training data has been poisoned. Right, so far what I talked was, a lot of the methods, research methods to actually attack and defend, but how do we actually do in real world? Is there code, right? So for that, we actually launched a tool in open source called Adversarial Robustness Toolbox, and it's a library, which is dedicated to adversarial machine learning, works across multiple frameworks, TensorFlow, Keras, PyTorch, MXNet, and the idea there is that, to allow you to rapidly craft attack methods, point it to your models or data sets, figure out, if there is vulnerability, and if there is vulnerability, then be able to give you different mechanisms, right? How do you actually defend against that? We started, from a focus on images because, that has been the field, which is most vulnerable right now to adversarial attacks, being able to generate some adversarial noise, insert it in your images, and being able to then fool the model, which is giving predictions, right? Now, as part of the next release, right, when we are watching towards 1.0, we are actually starting to work on some other input forms of data like text, speech, etc. So with that, this is essentially the surface area which the tool is covering, the Adversarial Robustness Toolbox, right? So being able to detect, vulnerabilities, being able to help you to craft attacks so that you can then, point it to your models and data sets. And if vulnerabilities are found, then being able to, give you code implementation of algorithms to defend, right? So 3 plus, the 4th dimension we are adding is actually being able to give, metrics to your trained models, right? So whether how much vulnerable they are to attacks based on what they have been trained on, whether it's the data or the model. So this is essentially, there is a very simple demo which I have, right? So one is, if you look at this, and maybe, it's best to sort of show it live if the internet is good. So it sort of clarifies, the concept behind this. But the idea is that, for example, let's choose an image here, right, which is a wheel, right? In this case, if you see, the model is, being able to predict for 97% that, it's a car wheel. Now, if we launch an attack, right, so one of the methods, for example, projected gradient descent, right, which actually introduces a lot of adversarial noise into this. And if we see, even if the intensity is low, the confidence of the model to predict that it's a car wheel has gone down to 26%. If we increase the intensity to medium, it's 10% confident now that it's, a car wheel. And some of the things, which probably are not very visible on the screen there is, it's actually, introducing noise. So you will see the image being perturbed. So it won't be, too visible on that projector. But now if I, increase the intensity to the max level, you see that, it's now predicting this is a violin, right? If you see the code behind this, right, it's essentially, we are using R to actually load the model, and then, creating a projected gradient descent attack methods, and then, pointing to the model, right? So this way you are able to find, your model is vulnerable to attack, right? Now, how can you actually then, fix this, right? So you can use different techniques like something like spatial smoothing. The idea there is, being able to blur, in layman terms, we are able to blur the image to the point that, you're smoothing the image. For those of you who work with Photoshop editors, you probably are doing it a lot of times, right, where you're actually reducing, the intensity of the pixels or the number of pixels because, most of the times models are smart enough to detect even if you don't have very high definition images, right? So in this case, if you reduce that number of pixels and reduce the surface area, then for an attacker, there is less area to exploit, right? So in this case, after introducing spatial smoothing, even at a low level, which is a defense mechanism, it's now 86% confident that it's car wheel, right? And if we make it, pretty high, we increase the confidence to 98%. Right. Another method is, feature squeezing, and the idea there is that, you then essentially are, reducing or, making the image a little bit sharpened, right? So removing some of the high intensity color pixels, but then, increasing the sharpness of the image, right, which essentially are being transported from some other parts of the image. So again, with both the techniques, the idea is that we are reducing the surface area on which the attack can be done, right, in this case. So that, in general, is an idea, behind this tool. The other aspect is, you can actually use that as part of your, Jupyter notebooks, right, in your pipelines, right? So in this case, for example, what you're seeing here is we have created a pipeline, right, where essentially we are using, Fabric for deep learning for model training. And then, after training the model, we are performing a robustness check, and based on the different conditions, so this shows better, right? So after training the model, we are performing robustness check, and based on the different conditions, right, we can either decide, whether we want to send the model for retraining after fixing it, or we want to deploy the model, right? So these are the ways. In this case, if I try to run this model, it's essentially, okay, so installing some of the packages, right, for the pipeline part of it. Okay. And then we are actually defining our pipeline that, we want to perform the training, we want to perform robustness check, and then, based on that, we want to deploy this pipeline, right? And we run that pipeline, and once it is deployed, right, it actually launches that, your pipeline has been launched. Now, this will take, so it starts with the training part of the pipeline, right? This will take a while, but, if there is a pipeline which I have run before, if I go to the experiments, right? So in this case, if you see, there is a pipeline, which I have run before. And in this case, what you're seeing is that, it did the training, right? It did the robustness check, and the output of the robustness check, and it's a little hard to see here, but it came down to 0.14%, right? And our threshold was 0.2, right? If the accuracy on adversarial sample falls below 0.2, we are going to retrain. So in this case, right, the test failed. It actually, started a retraining pipeline, after introducing adversarial examples, right? And then deployed the model, right? And finally, when the model is deployed. So that's the idea, behind these pipelines which we are using. I mean, and how you can introduce both, not only robustness check, but fairness check in your AI subsystems. And, there are different pipelines you can run it against. We are running it against a lot of our products in Watson Machine Learning, in our open source projects. And you can, go through them and use it in that manner. With that, I'll pass on to Svetlana, who is going to, go through some of the notebook samples and show you, outside of the pipeline, if you just want to use ART natively, how you can use it.
Thank you, Animesh. Hello, everyone. I'm Svetlana Levitan. I'm developer advocate at IBM. And today I will take you through some of the Jupyter notebooks with examples of the use of Adversarial Robustness Toolbox. So we all, of course, begin those notebooks with loading some libraries and necessary data. And all these notebooks can be found on public GitHub. They're all open source code. In this case, we import a ResNet 50 model, which is a well-known model. And we will use ImageNet dataset, which is a dataset with some closing. And here we can just see an example. We load this trench coat picture, and the original model classifies it as trench coat with confidence 1.0. Great. Now we apply a little bit of adversarial attack on it called projected gradient descent. You can see in the box. And suddenly this modified image, which if you look at it, you cannot see the difference, but the model now classifies it as military uniform with pretty high confidence. Now, if we also apply some defense methods on top of the adversarial attack, in this case, we are applying feature squeezing, which Animesh explained before. And now that we again get the correct classification. So in this case, the way to defend from this adversarial attack is just pre-processing of the input image. In this other example, we will use a different approach where we will use those modified images, the images that are produced using adversarial attack methods, to train the model. And the new model will be much more robust, and you will see in a few slides here. So in this case, this is a model which recognizes the handwritten digits, the standard relatively small model, but still has 225,000 parameters. And we apply this fast gradient, gradient method attack to the images, and then we can see that the original model classifies the original data with 100% accuracy, but on the adversarial processed inputs, our correct classification is only 20%. So now we will train a robust classifier, which is a new model that we have to train. And we also increase the number of units in a hidden layer, in one of the hidden layers, from 128 to 1024. This is all done based on this paper by Medri et al. And this modified, so here in the box you can see the code that was used to build this robust model. Of course, it takes a lot of time, so we cannot show you now because it would require some GPUs, and it will take some time to train this model, even though it's relatively small, but still, you know, it's a big model. This adversarial trainer method takes as one of the inputs the attacks that you want to include, and it builds the model for you. And with this robust classifier now, we still get 99% accuracy on the original data, and at the same time on this adversarially produced data, which, by the way, was produced with a different attack, not exactly the same attack that was used for training this model, you get 79% correctly classified, which seems much better than before, better than 20%, right? Okay, and now we also check how this robustness stands up to the different, to the varying levels of the adversarial noise. And it turns out that it's pretty good even when the attack is pretty strong. You still get about 80% accuracy on those modified images, which is very good. And now the third example here would be based on CFAR10 data, which is 60,000 images, color images, 32 by 32. And this data was collected by those famous people who came up with many of those things. So again, we load the data, and we are using ResNet 50 model. And this model, as you know, is much bigger than before. So here I just showed parts of that model. So altogether, there are about 50 layers. And the number of trainable parameters is almost 500,000. And here we show that the model is pretty accurate on the original data, so 98% accuracy. And here you can see some of the examples which are classified correctly. But if we apply adversarial attack to this data, and the attack in this case is fast gradient method, then again we get about 20% correctly only. And in this case, what we want to do is slightly different from before. We want to keep our original model unchanged, because maybe our users don't want the model to be changed. But at the same time, we want to protect against those attacks. So what can we do? We can build a detector model. So it's a new model that would be given an input image. It would decide whether this image has been adversarially modified or not. And if it has been, then instead of giving it to the original model, maybe we should go back and see where this adversarial example came from and figure out who is our adversary who is trying to give us this bad data and to confuse us. And if it's not adversarial attack, then we can just go and score it with the original model. Do the inference using original model. So in this case, we are using this binary input detector method from the Adversarial Robustness Toolbox library. And we build a model using that. And when we evaluate the detector, we can see that it works correctly with adversarial test cases. In this case, we even got 100% correct. And with the original data, we only got 2 wrong out of the 100, which is probably not too bad. And we should note that even when the strength of the attack is very low, we still can detect about 80% correctly. And of course, as the strength increases, we can detect even more cases correctly. Okay, so yeah, as I said, we will use the detector model to figure out when the cases should not be scored. And the advantage is that the original model will be kept unchanged. Okay, so the conclusions are that adversarial attacks do pose a serious threat to the deployment of artificial intelligence models, and especially in security-critical applications. And there is a lot of research work going on around this. In the future also, we are looking into dealing not only with image processing data, but also with other kinds of data. And this is an integral part of this overall trusted AI initiative, which also includes fairness, explainability, privacy, etc. And IBM Research has this website with lots of useful information. And also IBM, IBM GitHub has a lot of information about all those packages. It has all those open source packages. So again, we have looked at all this AI pipeline, and we talked about several things here, but mostly about art. And another thing I should mention today is that there is call for code. Anybody heard about call for code so far? No? Well, it's a global initiative, like 5-year initiative. The first competition was last year, and this year we have a second one. You can sign up at callforcode.org and use your great skills in data science, machine learning, programming, etc., to create some kind of applications that would help people affected by natural disasters. So this is a global initiative where IBM is a sponsor, and we work together with several other companies and with the American Red Cross and the United Nations. So it's huge. And actually, last year, I believe the top winning team got like $200,000 prize. So, and there are other prizes as well. And the solutions are now being implemented in real life to help people affected by natural disasters. So please go to this website and sign up and apply your skills to help people. Well, thank you very much, and we can take some questions, but we have about 2 minutes. We have microphones. Please let us know. Please ask your questions. And you didn't take a picture. Please do. Any questions?
So my question
Yes.
is, can these principles be extended to non-image data? Like if I have a normal continuous feature that satisfy the regression conditions, can we use these techniques for that kind of features?
So I believe your question is, can this be used for non-image based data? Yeah, so definitely, I mean, as I said, I mean, right now the release which we have for Adversarial Robustness Toolbox 0.6, the focus was on images. The next set of releases, we are targeting is, as mentioned, is, going to work across different kind of data, which is, text, speech, streaming data. But the techniques in general, yes, you can expand. For the tool, actually, the open source tool to actually provide that code, which can work with other types of data beyond the image. I mean, that's something, part of our, next release, yeah.
Any more questions? Thank you all very much.
Thanks for coming, and definitely,